Okay, so good afternoon, guys. And so, if you haven't noticed, I've posted some materials in our classroom, and that includes the lecture modules created by some of the faculty members of ECE. And that is somewhat of a summarized or condensed version of the contents of our handbooks. That is from Boylstad and the one from Floyd. And you might want to check that. No? Uh, Hopefully, that can provide you the okay, so the resources now for some of the problems or topics no, that we have covered. And also, the other is the lab manual. So, okay, so we will start with the lab activities, beginning with the experiment one for this week. No, but the activities, but for that activities, you're gonna perform the in the instruction in your own time. So, can I see a show of hands if you were able to access the materials? Okay, so thank you guys. Now, so if you can recall, I think I've instructed you last time to come up with your groupings, no? Okay, for the experiments, for the lab activities, you're gonna work with the same group, and we will start with experiment one. But again, we're not gonna perform this on the lecture hours, but you might want to check the instructions now. Uh, so there are various circuits that you're gonna build based on the instructions and the specifications provided. And it's okay. So for experiment one only, no. So it's up to you if you can if you want to perform this using software simulation or physical implementation. So you have that flexibility or option if you want to work on the actual stuff or the simulation. And that the outputs will be summarized in a report. The format of the report will be something that I'm gonna share later. So I'm gonna share that tomorrow, maybe in the afternoon or evening, once I'm done with all the lectures for this week. No, so but okay. So for this week we'll have the experiment one, and that you're gonna work in groups of. I think I've set a maximum of 5 members for this, or at least Yeah, so since there are 41 of you guys, I think one group will, I'm okay with one group having 6 members, no? But all the others can have five members. Well, if some people would like to work in smaller groups, then it's up to you. It's okay naman. But I'm expecting at least 8 groups for this batch or for this block. Is that okay with everyone? Yes?
Hello po sir, bale nagkaroon na po kasi kami ng groupings pero ayusin ko po kasi maximum of 5 po pala yung ano, ang nagawa po namin ay tigsa 7 members po.
Yes, yes. No. So 5 members. There will be one exception where I will allow a six member because you are 41. No? So I'm expecting at least eight teams. Yeah, eight groups for this block. Except for some cases where some would like to work in fewer groups, then that's the exception. Then when we're gonna have more than 8 groups if that's the case. But at least I'm expecting at least 8 groups for this block, and hopefully you can consolidate that uh, within this weekend. No? So I'll just update my records, for your groupings. All right. So okay. So thank you, and okay. So for now, please check the instructions now if you have any questions, and then I'll give you guys maybe 5 minutes or so to check the instructions. No? And if you have questions or concerns, you can just post it in the chat box. Before we proceed with the continuation of our lecture for the day. Okay, so any questions or concerns so far with the yes?
Sir, hindi naman po sa experiment pero i-clarify ko lang po, yung groupings po namin sa mga experiment, yun din po sa final paper.
Yes. No? So I think that will be more convenient for us, no, to come up with the same group for all the other
Thank you
activities.
po, sir.
Okay, so also okay, so today we will continue with our discussion on the DC analysis of transistors. No? So tomorrow we will uh, have the AC analysis, but we will just try to finish the DCA sections for now. Okay, so the format for the report on the experiment will be shared tomorrow, once I post the submission link. I'll also provide the details on the submission. But expect that you're gonna do some side research for the report, and that you'll gonna have to start practicing the technical reporting format using the triple E template, no, in the case of the experiments. Anyway, the final paper for our the term paper, no, for our final project will be presented in the same format. No? So this is another exercise for you to be familiarized with such presentations. Okay, so I guess we can proceed with our lectures. And also, I'm thinking of scheduling our first quiz next week, because yeah, so we are required to come up with at least, I think, two quizzes for this term. And the coverage of the first quiz will be from well, the introduction and the semiconductor discussions until this topic, no, the DC analysis for the transistors. Okay, so yeah, so for the DC analysis, so I'm thinking of setting a synchronized schedule for all the sections that I handle, and I think the based on the schedules that you've shared with me, a solution is to schedule the quiz on Sunday afternoon. So that will be okay. So I think I've deleted it. Okay, so that will be on March 3, Sunday, from 2 to 5 p.m. So, well, the intention is to synchronize all the sections that I handle, and so we can maintain the integrity of the exam, no, through such basis. Okay, are there any conflicts with this schedule proposed? Yes.
Hello po, sir. Bale, face-to-face po siya.
No need, only online. All the exams
Okay.
are online. Yeah. Uh,
So, wala naman pong conflict.
okay. Okay, so the only face-to-face session, because we are as instructors, no, doing the online modes, we are required to at least come up with one or two online sessions, for the entire term. So I reserve that online session for our projects, no. So there will be two. The first is the proposal presentation. So you will come up with your um, concept paper, no, project concept paper. So again, like in the thesis, you have the title defense. anyway, this is not as extensive as thesis. This will just be a term project. But at least in that section, you're gonna do some presentation for your proposal, no, or your concept or your project concept. I'm thinking of that in to be done in I don't know, March 16. I've yet to check if that is feasible on March 16 or around that week maybe. No. And then the final project presentation will be on. Although initially I set it at week 15, but I think I'm gonna swap it with your final exam. So your final, because I'm out of town by May 4 and 5. So I guess I can schedule your final exam by week 15. So you guys will have our final exam way earlier than scheduled, because the finals we will have the project presentation on maybe May 11 or 12 on week 16. Yeah, so you have the project concept presented on week 8 and the final presentation at week 16. So that's the schedule that I'm currently thinking. No? So yeah, so any conflicts with the proposed schedule?
Hello po sir. Hindi po related dun sa schedule. Pero sir, pwede po namin maitanong if ever kung ano po ang magiging types po ng mga exams po namin.
Okay, so since I'm thinking that all of your exams will be MCQs, because you will be uh, the expectation is you will be burdened already with the term papers, and then you still have the lab activities. So yeah, so all the exams, my intention is that all exams will be conducted in MCQ format. And for MCQs, well, although you're not required now for the board courses, then similar to the same questions that is being used in the case of electrical or electronic board exams, that is aligned with 421. Yeah, so maybe that there are some calculations, fee calculations involved, but my intention is to have all of this in MCQ formats. All right. So any other questions or concerns? Yes.
Sir, ask ko lang po, nagpuputol-putol lang po sa akin kanina. Yung lab 1 po, hanggang kailan po ang pasa? Kailan po ang submission?
Okay. So for lab one, we we will have the experiment one, no, based on the manual. The submission will be next week. Yeah, so next week.
Thank you
I'll
po.
post the
Thank you po.
submission link. Yeah, but you have an entire week to complete that. And it's up to you, no, to decide whether you want to do a software analysis or an actual implementation. So since because we're on online mode, and you have that liberty. Yes, again.
Hello po. Bale, may susundin po ba kaming format para po sa presentation po ng mga experiments at gano'n na din po dun sa final paper po na gagawin.
Yes, no. For the presentation format, you will follow the triple E conference paper. So the one I've shared. I will also present a link once I posted the submission link. No, I'll also present uh, include a link that will direct you to the template, yeah, for the triple E. All right. So, is there anything else before we proceed with the lectures? Okay. So, if none, then we'll just finish the DC analysis section of our lectures that we have started last week. No? So, last week we have covered the DC analysis for the BJT. No? So, right now we will proceed with the FET naman. And that so tomorrow we can start with the AC. Right, so we'll finish the DC today, so we can have the AC analysis tomorrow. And some essential relationships that we need to remember when doing the DC analysis for FET are the following. No? Since we have defined FET as having uh, zero current at the gate, no, for MOSFETs, that is also especially true. Anyway, these are valid for both JFETs and MOSFETs. And that the current going through the drain is the same as the current going through the source. All right. And the Shockley's equation applies for both FETs and the depletion type MOSFET. But not for the enhancement type. So that's something that we need to recall, no, every time we do or we perform circuit analysis. In a sense that if we make sense of this equation, the greater the amount of the gate to source or the gate voltage is, or once we reach the gate, the gate voltage reach the pinch off threshold or the pinch of voltage, then we have essentially a drain current equivalent to the saturation. So we essentially omitted this. On the other side, for the enhancement type, uh, we are essentially increasing naman on the other hand the voltage, the gate voltage with the reference to the threshold. No? So we need to reach the threshold voltage to come up with, with the current here, and then yeah. So that is because so in the case of enhancement uh, type, we are essentially adding or increasing the channel width, no, with the increase of voltage applied as well as opposed to the depletion type. Okay, so we will start our analysis with the simple fixed bias configuration. As we can remember, the same uh, wiring connections is true for the case of BJT. But in this case, instead, we have a negative supply for the gate. So this is the key difference, no, between the FET and its BJT counterpart. In the sense that, okay, so we go back to the properties. The gate current is zero in all cases of FETs. And that if we try to solve for the voltage across the resistance right here, no? Then we will need the gate current times the resistance value. And since we don't have any current going to the gate, then the voltage across the resistor RG, let me go back, here is 0 as well. So we do not essentially perform uh, analysis for the in consideration of the gate current. But applying KVL through this loop right here, we can see that if we are to supply negative voltage here, then there will be some voltage drop across the gate to source pins. So essentially, VGG, or the supply voltage here, is essentially equal to your VGS, or well, negative to your VGS. All right, so okay, so next is to proceed with the analysis of the output loop, and that is through the drain to source network. Here we make use of the equation of Shockley, and that we introduce values that is in various values of IDs or VGs. No? So say for example, if IDSS is typically presented in data sheets, so this is immediately available. Pinch of voltage is similarly included in the data sheets. What we need to solve for is the values of ID for the Q points, and as well as the VDS, no, the voltage across the transistor itself, which sorts of give us idea what the voltage output is when viewed from the pin D, or viewed from the outside going into the drain pins of the transistors. So some common analysis includes the half current, well, not really half power point, but half of the current span of the saturation in the quarter, and the case where you have a zero drain current right there. And in most cases, this translates to well, if you have drain to source saturation current, you have zero VGS, or zero voltage drop across. A zero voltage applied at the gate to source translate to the saturation current at around 0.3 of the pinch of voltage translates to half of the drain to source saturation current. Half of the pinch of voltage translates to quarter of the saturation current, again on the drain to source. And in the case of pinch of voltage, you have essentially zero drain current. And that point, then you can plot the load line to perform your analysis by doing or analyzing the intersections at which the load line and the applied voltages and resulting drain currents are related. So here's some example of an analysis in the output loop. Now the drain to source voltage of output can be determined using KVL. Here, performing KVL in this loop, we have the following: VDD minus IDRD right here, and the drain to source voltage. Again, that's across the transistor. Rearranging, since uh, we want to solve for the VDS. Since this is for the common emitter common source configuration, this is directly connected to the output. All right, so and since in this fixed bias configuration, we do not have any resistance connected in the source to the ground, so this is essentially zero. VD is equal to your VDS, so it's kind of the same thing. VG is essentially the same thing as your VGS as well. So one way to verify if our calculations are correct is to measure the current between the supply and the drain pins, as well as the voltage drop across the gate and source pins. No? So if I measure that and matches your calculation, then you may have came up with the correct design figures. So say, for example, you're working on the sample problem right here. So we have the drain to source saturation current and the pinch off voltage as a given. Okay, so here, since we have the voltage supply at the gate at negative 2 volts. Again, what we are saying is that since the current here is essentially zero, the gate pin essentially sees the supply as it is now without any voltage drop at exactly negative 2 volts. The drain current can be obtained from the Shapley's equation, considering the input at negative 2 volts, we can come up with the drain current. The drain to source voltage or the drop across the transistor can now be calculated given the drain current at Q point. So Q point is essentially just what we're saying is that we don't have any sort of AC input in the Q point. And we came up with 4.75 for the drain to source voltage. Drain voltage is essentially the same as your drain to source voltage. Again, since you do not have any resistor here to take up any voltage drops. In some other configuration, we're gonna cover that particular case. But to proceed, again, we have the gate voltage equal to your gate to source voltage, and that source voltage is at 0 volt right here. Right. So again, we don't have to have any component in the source connection. All right. So self-bias configuration eliminates the need for two DC supplies in a sense that when we've introduced a resistance RS here at the source connection, let's try to go back now to the fixed bias. So instead of having a supply here, we've eliminated the supply and just install a resistance here. So that's the difference. That essentially when we were doing analysis in a KVL in this load section, this resistor plays its part, no, in providing some bias at the gate pin. And this will be apparent later when we run through the calculations. So again, in this case, still have the gate current at zero and the voltage across gate resistance, which is emitted here, is also zero. The current through the source resistance is IS, but since we've established that source current is essentially the same as your drain current, then we can just use these things interchangeably. that the voltage across the external source resistance is equal to ID times RS. Then performing KVL for the gate source loop right here. We have VGS minus VRS right there. So even if we have the resistor, so it doesn't play any part in this analysis because the current at I'll have to go back. The current at RG is essentially zero in this analysis. Right, so now we can start solving for the drain current based on the equation of Shockley. But one thing we can take note at this point is that the VGS right here can be expressed in terms of ID and RS right there. So since we don't have the value of VGS right here, remember guys, this is not BGT, no, that this is in BGT. The base to emitter is immediately available as zero point 0.7 or so. So that is not the case here since we have to perform a different calculation in this one. And this is given by this expression IDRS right there. So in KVL, the voltage drop here matches the voltage drop here. So we plug in this expression in the original equation. So this becomes a plus value. Take note of that when you're doing your calculations. No? And then what we can see here is that IDSS right here is provided by the data sheet as well as your pinch of voltage right here. RS is given by it's provided by your design. Now you have two sets of ID values in this equation, and it's in a second degree. So we can calculate this using quadratic formula if that suits you, or calculators. No? Just do a shift solve and we're good. No? Once we can come up with the ID values. Now for the output loop, that is to say the drain source voltage, we perform KVL also similarly at this point. VDD minus ID, RD minus VDS minus VRS right here. Now rearranging the equations, we have the following. And then what we can take note of this is that ISRS here is 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 equal to ID, so we can move that out, and this can be lumped together, the effects of RD and RS, and VDD and VDD is a given. IDD is something that we can obtain from Shockley's equation. VS right here is again IDRS, no? IDRSI or ISRS is kind of the same thing. VG is always consistently 0 for FETs. VD here is now VDS minus VS. So that's the difference between the fixed bias. So for the fixed bias, you don't have any components in the source connection. But in the self-bias, this will be included in the calculation. And that the VDD, or the VD right here, is equal to VDD minus IDRD. So VD at this point is where you tap your output. No? So it provides the DC steady level in the case of zero AC input. Okay, so let's look into the following example for some actual calculations. So kindly check the calculations involved. No? For the first one, we have this loop, and the second one, we have uh, always in these cases, no, we have the input and the output loops. All right, so for this case, we've seen the KVL performed at this point. Again, we do not include this in the equation considering the fact that we have zero current at the gate. You know? So we just have the VGS as equal to the drop across the resistance here. And then uh, using this expression, we can plug this in into the Shockley's equation. The resulting equation from Shockley's is that of a second order. You can use shift solve for this case and then come up with the drain current. Now, once you have the drain current, we can go back to the VGS value here, and we can have the VGS now at this part. So once you have the VGS, we can now proceed with the drain to source now in this case. Right, so once you have the okay, so anyway, once you have the drain current, you can now proceed actually with the load with, with the well, with the loop analysis in the load side. So here we have performing KVL. We have 20 minus IDRD minus VDS minus VRS. Now, rearranging these terms, we can have this equation here. So we have 20 minus ID RD. We now have ID here. And RD. You have the VDS transpose at the left side already. And then ISRS is right here. And since IS is essentially same thing as your ID, we can lump these two things together. Then we can come up with the VDS value at 8.8. Now, for the source voltage or the voltage across RS here, and just plug in the values of ID and RS directly. And we have VS at 2.59. Okay, so, yeah, so since you have 1K here, coincidentally you have the same 2.59 there. And again and again, we have voltage at 0. So VD is equal to VDS plus VS right there. And doing a load line analysis, since we are at IDSS or the saturation current at 8 milliamps, we can select maximum and half points to come up or solve for the VGS values. Now for the case of half current, and then the voltage uh, across this across the VGS is at -4 as well, and for the saturation condition VGS is at -8, and we can see that in the load line here. Here we have a trivial solution, so since we have 0 VGS at 0 ID. And further exploring the drain current characteristics, we have the following from the Shockley's equation. So the Shockley's equation presents a curve where we can plot the Q point based from the load line analysis. So from Shockley's equation, we can figure the VGS value at Q point, no, or at 0 AC input to be at 2.6. So that's what happens when we rearrange these equations and come up or go back to this. So since we have already the ID, we have about 2.6, and the current here will be right. So the current here will be 2.6 as well. Okay, so just looking at the plot. Anyway, analytically, you can come up with the same answers, no, in the Shockley's equation. Okay, so next is the self. Okay. Okay, so for the other values, we have the drain to source voltage based from the original KBL. Source voltage is at Q point, can be obtained from the new value of ID here, no? So it's on IDQ. And for the VD, again at Q point, then we just add these two things, VDS and VS at 11 volts. So what this means is that at Q point, you have a constant DC from measured across the drain pin to the output. Anyway, this DC cannot be seen from the output pins, no? Because again, I think we mentioned of the capacitors last time. No? So the capacitors essentially provides isolation for the DC. So all the DC components are contained within the right of C1 here and the left of C2 here, as well as the upside of CS right there. So again, in the context of DC analysis, we do not see yet the value of this uh, capacitance. These are significant now when we go to do the AC analysis. But for now, take a look or consider the following configuration for the voltage divider. So similarly, we can come up with the voltage divider for FETs. And that this provides a similar bias point for the gate to source voltage using the resistance networks R1 and R2 right there. So kindly look into the configuration and we'll go through the analysis. Okay, so similar to the BJT counterpart of the voltage divider bias, we're gonna have to separate the input circuit of the output circuit first by doing the uh, voltage divider calculation across R1 and R2. And of course, here we have the voltage across the at point at the gate as your VDD divided by or multiplied by R2 divided by the combined resistance. So that's how we perform the voltage divider. And after that, so similarly, we can perform analysis in this VGS loop before proceeding with the output loop right here. So kindly check the equations and properties that we need to figure, some of which are very much similar with the self-bias configuration that we've seen earlier. So once we are able to reduce the equivalent voltage across the output right here, this is essentially uh, very much the same as your self-bias, no? In the previous example. Okay, so is everything clear with the calculation presented? So essentially here we are just doing the same thing here. VG at this loop is equal to VGS minus VRS right here. And that VGS is equal to, well, just the equation is just being rearranged in this case. So what we need to solve for now is the uh, VGS and IB, and that we'll go through the uh, so the load line analysis for this one. Here, for the voltage divider bias, in this case, in in the case of zero drain current, we can see some positive gate voltage already, right? Okay, so some positive VG at uh, zero drain current because of the introduction of the biasing here. So it sort of offsets, no? So in the self-bias configuration, you have the trivial solution here. Here you have some offset at ID zero because of the voltage as the effect of the voltage divider. So we can plot similarly the drain current, the curve or the characteristic curve from Shangle's equation, and come up with the Q point in the or using the intersection of the load line and the drain current characteristics. Now, similarly, that can be obtained, no, from rearranging the equation or the result of Shockley's equation. But we're gonna demonstrate more of that later. No? So for now, we will solve for the load side. We have VDD minus IDRD right here, and drain to source voltage drop, as well as the voltage drop across the resistance external source resistance VRS right there. So we have another KVL at this side, and rearranging that, and assuming since we've considered drain current and source current as of the same value, we reduce that into the following equation. So we've lumped the drain resistance and the source resistance together. So the source voltage is equal to the drain current across the source resistance as well. No? So it's kind of the same thing. And again, the gate voltage is from the input network right here. So it's essentially non-zero, no? In the case of voltage divider bias. And that the voltage at the drain terminal is equal to VDS plus VS. Similarly, we can obtain that using VDD minus IDRD as well. No? So we can come up with the same figures by subtracting this one, because essentially what remains is the same here. All right, so yeah, so that's the thing we need to come up with, the drain current at Q point and the voltage, drain voltage, because that's the voltage across the drain is what where we're gonna tap our output. Okay, so for some practical examples, we look into the following. So here we have the resistors in the network provided. And from the data sheet, we can obtain the drain to source saturation current at the pinch of voltage of -4. All right, so a bit lengthy solution, but here is the explanation. For the input network, we have the voltage divider across R1 and R2. The gate obtains input voltage from across R2. So that is 1.82, based on the voltage divider network right here. Next is we perform KVL to the VGS input loop, the gate input loop. So VG at this point, or the voltage across R2 is the same as that. So VG minus VGS minus the source resistance here is equal to 0. So that's your KVL for this loop. Rearranging, we have the following uh, okay, so rearranging that, we have the following equation. VGS is equal to VG, which we obtained already in this section, minus ID, which we've yet to define at Q point, times the RS value at 1.5K right here, right? So we can now go to Shockley's equation. And since we have two unknowns here, we just plug in the VGS here, VGS expression here. We can plug in directly into the Shockley's equation and come up with this second equation here, from Shockley, which we only have the drain current variable remaining. Although this is already in a second degree, then we can just again hit shift solve in our calculators and come up with the drain current at 2.42 milliamps. All right, so once we have the drain current, again, we can now perform the analysis in the load side, which is your VDD minus IDRD minus VDS minus VRS. Right, so when those terms are rearranged, then we can solve. Sorry, I think I skipped this first part. No? Okay, so this first part pa muna. So for the gate to source voltage, we have the gate voltage at 1.882. Alright, so some deviation here, but this is the same thing. The gate voltage here at 1.82 minus IDRS. No? IS is same as ID, so you have IDRS. And so we can have, once we have the ID here, we can have the VGS at negative 1.81. As for the VD, which is directly connected to the output, again, we have the output loop, which I've already mentioned. And the VD is at 10.19. So you have a 16 volt for VDD. RD is obtained here already at 2.42. RD and our RD is a given, so yeah, so we can come up with a VD right there at 10.19. So what this essentially means is that the voltage VD 10.19 volts is maintained at drain once you turn on the amplifier, even with the input at 0. So what happens is that, recalling from the mnemonics I've shared previously, uh, the disco, no? In the DC, inductor is shorted, capacitor is open. The DC supply of 10 volts from the drain connector here is not being measured in the output actually. So we only have a DC reference here. So this lifts the output at some 10 volts above zero, no? So that's what it means. But after this capacitor, this is zero already because in DC, this is essentially open. But when an AC signal comes in, well, more on the analysis in the next session. But when again, when the AC signal comes in, an amplified AC component will be superimposed on that 10 volts. No? So that a larger version of the AC will be riding on top of the 10 volts output here. And that component can now pass through the AC, the larger AC component can now pass through the capacitor because the capacitor acts as a bypass for AC signals. Right? So in DC, inductor is shorted, capacitor is open, but in AC or higher frequencies, it's the other way around. The capacitor acts as an open circuit or a high impedance component, while the capacitor acts as a short or a low impedance component, allowing the AC signal to pass through the BO right here. So that's how some snippets of the amplifying action in this configuration. All right, so again, for the VD, that's it, no? While for the VDS, we just subtract VD minus VS, and VS can be obtained already in IDRS since we have the ID already. So VDS is at 8.37 volts. So take note, no, that in DC analysis we have the VD as reference, but we need to solve for the VDS because this is useful in AC analysis. In AC analysis, what is viewed from the output is the what will be the reference or maximum voltage swing that you can utilize is this VDS value. Because in AC, you're gonna bypass again this source resistance. So essentially in AC analysis, this is nothing. You just see the capacitor right here as a bypass path. And so the voltage drop across RS is not being considered. Right? So hopefully you're starting to build the idea now of how, okay, so of how transistor action is being realized, no, in this in the combination of the DC amplification and the AC later. Right, so more on the load line characteristics can be described in the following. No? Just for now, just check it to or check the load line characteristics for the Q point conditions and the other ID values, combination of ID and VGS values. Okay, so considering the load line analysis, then we can now have, okay, so for the various values of VGS at different values of ID. In the case of pinch off voltage, you have zero drain current. While for the zero VGS, then you have the drain to source saturation current. And then at point 3 pinch off voltage, you have the half current point, and at point 5 um, pinch off voltage, you have the uh, quarter of the drain to source saturation current. So that's around. So at 1.8 here, we have 1.8 VGS. You have 2.4 milliamps drain current, and that is your Q point now, where the load line touches the uh, characteristic curve, no, for your VGS and drain current. Right, so for the voltage at the drain point, now we have the drain current. We can now obtain the VD, so it's at 10.24. And so for the voltage across the RS right here, once you have the VD at 2.4, you can have the source voltage at 3.6 volts. So for the VDS, it should be again, this will be useful for the AC analysis. Then we have it with the 2.4 ID value at 6.64 volts. And right, so for VDG, we have it at 8.42 volts. Now, another thing is the common gate configuration. No, this is the analogous to our common base configuration. And in this case, we have supply for both the drain and source connections, while the gate is directly connected to the ground. So in this case, we apply the input through our source right here. No, so you see the source network right here. So the input loop is through VI right here through the RS and your supply, while the VO loop is from the VDD and then the RD going to VO right there. So rearranging the circuit in the usual sense that we have the inputs in the left hand side and the outputs at the right hand side, we have the following, and all of these pins are commonly connected to a same ground, and that the gate, no, is the one common to both the inputs and outputs. Now we perform KVL in first in the input for the VGS. We have negative VGS right here minus ISRS plus your supply VSS right there. Then rearranging the equations, we can have the VGS at VSS. So it's this is a given, and we'll try to solve for IS later. But VSS and RS are given in both conditions. In the case of, we're gonna do another load line analysis in this case. So for the scenario of zero drain current, we have VGS at VSS. No? So zero drain current, right? So at zero drain current, we have VGS as equal to VSS. Yeah, so for the zero drain current, VGS right here is equal to ESS, since we have that same loop right there. And in the condition of VGS 0, ID is plotted as your right. So ID is plotted as your VSS over RS. VSS over RS. Since ID is equal to ID is equal to your IS as well. So well, plotting that curve ID is equal to VSS, or plotting that line ID is equal to VSS over RS, we have the following. Now from the Shockley's equation, we can plot this curve right here. And once we've met the intersection for these 2 points, then we can have the Q point values at VGS and ID. While similarly, through analytical techniques, and then we can just be able to come up with the same values here from the Shockley's equation. For the loop, for the KVL around the loop, no, or between the inputs and outputs, we have the following: VDD is equal, or VDD minus IDRD minus VDS minus ISRS minus VSS is equal to 0. Since IS is equal to ID, we can lump or combine similar things together. So that here VD becomes VDD minus IDRD. Similarly, VS becomes VSS minus IDRS right there. So the loop, I can think of a loop going this side. Now VDS is similarly VD minus VS. So the difference between the in common gate configuration of VO minus VI in this case. So let's try to work on some example. Given the drain to source saturation current at 12 milliamps and pinch off voltage at negative 6. In this case, we don't have VSS supply. So this is a zero case. So considering it's for the pure computation case, we have the following. Then your VGS is equal to VRS. VRS is equal to IDRS or ISRS. Again, kind of the same thing. And then we'll just gonna solve for, or we have two unknowns here, VGS and the drain current. We can plug in, substitute this expression again into our Shockley's equation. So the Shockley's equation can be simplified as having only one variable to solve for. Just hit shift solve for the second degree problem, and then we'll come up with the drain current at 3.84. We'll use this value for the drain current to solve again for the VGS at the input loop. So VGS is equal to ID RS. Since we have the ID already, we can solve for VGS, and it turns out to be negative 2.6. So similarly for the input and output loop, we have VD. Well, this is for the output loop. VD is equal to VDD minus IDRD. Since we have ID already, then we just plug in all the values, and the VD is at 6.2 24. Excuse me. So VS is also obtained from ID. And so in this case, we have VS at 2.6. VG is directly connected to the ground, so we have a VG at 0. VDS, which is will be the output component, or the DC component of your output, will be VD minus VS. Since we have those already, we have VDS at 3.63 volts. Right, so performing the load line analysis for this, so for various values of ID, so IDSS, since IDSS is 12, we will start with the half point at 6 milliamps. The VGS will result to negative 4.8 for 0.8. While at 3 milliamps, VGS becomes 2.6, no? Or negative 2.6. Oh, sorry. VGS becomes negative. All right, so VGS 3 milliamps is at point 0.5, no? All right, so VGS is zero point 0.3, so zero point 0.3 of negative 6 volts is at 1.8. Now, in the case of 3.8 milliamps, well, for the solution of this one, VGS is at 2.6 or negative 2.6. So that's for the Q point or the off condition, meaning we don't have any AC inputs on. VGS is negative 2.6, while ID is 3.8. So that's at Q point. Okay, so further for the drain pin, we have the voltage obtained from the 3.8 milliamp points here. No, again, that's in the Q point condition. So the drain voltage is at 6.3. Using the same ID value, we can solve for the VS at 2.58. Again, gate is connected to the ground, so it has a zero potential. And VDS is the difference between the VD and VS. Hence, we have the voltage across this pins at 3.72. And that's it, no? FET's configurations. Now we can move on to MOSFETs, and we'll work with first with the depletion type, which is essentially the calculations are very much similar to our FETs. So in this case, we'll just proceed with the calculation for. Right, so for this case, we have the voltage divider bias. We'll go through the KVL for the voltage divider network, and then the input network through the VGS, through the GS loop, and the output network through the DS loop. So take a look at the equation, and we'll go through the steps, no, for the case of D-type MOSFET. Okay, so what we can see here is that in the case of the depletion type, the same calculations were followed, no? Like in our JFETs. The first one is for the voltage divider. We just solve for the voltage across this one. So at R2, you can see that the difference in the resistance values is at roughly uh, some 10 is to 1 almost ratio. So the voltage drop across R2 will be at around that figure. So we see 1.5 volts at R2, which is will be your VG as well. So doing KVL at the input side, well, this is to relate VG to that of VGS and VRS. Then we can have an equation for this one. Further simplifying, we can express VG in terms of uh, ID because all the others are already given. And then we can plug in the expression for VGS into our Shockley's equation. No? Right, so for the Shockley's equation, we have the IDS as given and the pinch of voltage. Then we have an equation with one unknown, and maybe you can use quadratic formula or for calculator, just hit shift solve and come up with the drain current at 3.12 milliamps. So in the for the gate to source voltage, we can plug in now the new value of the value of drain current into this original equation and come up with the gate to source voltage here at negative 0.84 volts at this point. And so we can solve for VDS using the output loop. So based on the calculation, we can now plug in also the value of ID here. And VDS is set at 10 volts. No? 10 volts. So meaning in the off condition, you have a 10 volts here, isolated by the capacitor, the output sees nothing. No? But this sorts of maintains that elevated output so as to allow for swings, no? Brought about by the input sinusoids. All right, so yeah, so that's pretty much it. We have the VG figures. No, okay, so VG on the other hand is maintained at 1.5, no, for the first calculation. So meaning in the off condition, you can always measure 1.5 also, 1.5 volts also in this side. So what happens in the amplifying action is that when you input an AC component here, the small AC value will be superimposed on top of the 1.5 volts. So you have a baseline of 1.5 volts uh, with the AC small AC signal on top of it. Now, this small AC variation creates a huge variation in the drain current in this case. So that huge drain current is translated to huge amount of AC component as well in the drain voltage or VD or VDS. Now, this huge AC component can pass through the C2 capacitor here, no? Because C2 acts as a short circuit for high frequency components. So that is how this how amplification takes place, no? With the separate DC and AC analysis. Tomorrow, no, we'll cover the AC components of this analysis. Now, for the transfer characteristics, we look into the various values of IDs at half point and the quarter points of IDSS. Since we have IDSS at 6, we look into ID at 3 milliamps. And okay, in this case, we look only in the 4 milliamps. No? So at IDSS over 4 or 1.5 milliamps. And here we see that, okay, so at this point, VGS is at VP over 2, or negative 3. Okay, so VGS is at VP over 2 or negative 3 volts over 2 at negative 1.5. So you have the Q point plotted in this case for the 1.5 milliamps. All right, so okay, so right, so for the ID, no, at 3.1 milliamps, no, we can plot the Q point, and here the VGS is where we do have the figures here at negative 0.84 volts right there. So yeah, so again, that's the intersection of the load line analysis as that of the characteristic curves for the drain current and VGS voltages. So without plotting, no, just plugging in the values of the VGS or at these points, now we can see some values of drain currents and VGS, or across different values of VGS. Right, so in this case, okay, so for 1 volt at the VGS, ID becomes 10.6 milliamps. Okay, so that's it now. So based on the graph, I can come up with the Q point values. So similarly, from analytical techniques or without without plotting, you can you can solve for these values. Uh, so this is essentially we're doing the calculation voltage divider, then the VGS here. So we have ID missing here. So we have to assume different values. First is one is when the case of ID is equal to 0. Here we have VGS at, what should that be? Positive 1.5 volts. So this is a straight line right here now. Okay, so you have the plot from the Shockley's equation in this exponential, and then the straight line for the load line analysis is with the VGS and excuse me, VD relationship right there. So for ID0, the input loop at VGS becomes 1.5. Now, excuse me, at VGS is equal to 0, the ID becomes 2 milliamps. So you have an equation at this point. So this is another equation, VGRS at this point. ID is equal to VG at this point, and then you have, excuse me, you have right. So you have the straight line at this point, no? Uh, from the plots of 2 milliamps and 1.5 volts. So we can have in this yeah, similarly in this intersection the values of 3.1 and VGS at zero point 0.8 volts right here. Now in this case, we can solve similarly for VDS using the output loop VDD minus IDRD minus ISRS or IDRS, and we can come up with the same, around the same thing, no? 10, 10 very little difference with the graphical method and the analytical ones at 10.4 volts. Now, for the case of RS at 150 volts, I think there's some typo in the succeeding equations, but I'll just try to correct this for your. Yeah, so I'm gonna do some correction on this. But what essentially is being done here is that for different values of RS, no, or a lower value of RS, yeah, we can do the analytical, same analytical approach. For the transfer characteristics, a plot can be defined by IDSS over 4, which is at 6 milliamps. Over 4. So this will be at 1.5 milliamps. And VGS at half of the pinch off at 1.5. And so it's not directly plotted here, but okay, so well, in analytical techniques, then you can just substitute the values and come up with the same approximates, no? For well, that is to compare the graphical and analytical techniques. Okay, so similarly, to get to the Q point value setting, do we have the graph here? Oh, no more graphs. The drain current at 0. For the drain current at 0, we have VGS at 1.5. Okay, so that's for the drain current at 0, we have VGS at excuse me, at 1.5, or VG at 1.5. Right, so yeah. While for the VGS at 0, we can have the drain current at 10 milliamps. So once we have that 10 milliamps at 0 VGS, that's when we can plot this line right here. Right, so again at VGS at 1.5, you have the Q point or ID at 0. And then VGS at 0, we have ID at 10 milliamps. So we can plot the load line and solving for the intersection with the Shockley's equation, we can come up with the Q point and the values of ID and VGS at that point. Yeah, so that's what's being done here. No? So we can achieve or reach Q point from the graph as well as your VDS, no, at 3.18. Right, so okay, so in a different problem, we have that we'll solve for the drain current and the VGS and the VDS. So in any in most cases naman for FETs, we just look for these two figures because this determines the output parameters. No? So the currents at the drain and the VGS. Well, the VGS for the input and the VDS for the output. Okay, so here we have VGS as equal to VRS as well, and we have the same expression for VGS, which we will again plug into the Shockley's equation. So the Shockley's equation becomes second degree equation or in quadratic uh, form, or can be expressed in quadratic form. So which we can just solve using calculator. No? And then uh, after we figure the value of drain current, we will solve for the gate to source voltage using the drain current. And we see here that the input is maintained at negative zero point 0.4 volts at this side. No? So the VGS is at negative 4.2. All right, so and solving for the output loop, once we have again the ID here, everything else is provided in the circuit, VDD, RD, RS. We have the VDS at 4.78 ohms in this case. All right, so for the load line analysis of this one, since we have, so this is not a voltage divider, so we have a trivial solution for this. We have zero drain current for VGS 0. Now, VGS can be defined as uh, or described as same as your IDRS. No? So that VGS should be negative, and is therefore no. So we do not need to plot this now because we already have positive value and the trivial solution for the zero ID and ID and the VP or VGS. So assuming values of drain currents for the quarter case, we have 8 milliamps. Divided by 2, and then we have 2 milliamps the following. In the case of VGS, half power of VGS, we have, or half voltage of VGS, we have negative 4 volts. So this sorts of have the, the drain current and the VGS at that point. Okay, so for the case of VGS greater than 0, since VP is at negative 8, we will use uh, say for example 8 or a positive 2 volts, no, along that along the curve from the Shockley's equation. And the drain current at that point will be 12.5 milliamps. So again, that's in the case of VGS greater than 0. To get to the Q point, we set the drain current at 0, and the result is that VGS is also equal to 0. So for VGS at negative 6, we have ID at 2.5 no, in this case. So we can plot now the load line for this case. So the resulting Q point from the intersection of this equation is that ID is at 1.7 and VGS is at negative 4.3 right here. So we can obtain the Q point from the plot here. So once we plotted and have the bias line, then we can identify the intersection or the solution as our Q points. Solving for the drain voltage or the voltage output, we have the output loop at VDD, output loop KVL as the following. VDD minus IDRD is equal to your VD. So that becomes 9.46 volts. And so how about for the following, this is it's a self bias. We don't have RS for this case, and IDSS is at 10 milliamps. Pitch of voltage is at negative 4. So just through pure computation, uh, for 0 VGS, when we know that ID is equal to IDSS, then ID is at 10 milliamps. And so should be some sort of a This we're gonna have to recheck the calculation for this, but here we can solve for the VDS at, let's we have the following given at 5 volts. So we have the output at 5 volts, and that the between the gate and source, so you have some bypass in that case. So VGS is at 0, so meaning it's fixed at 0, and the drain current must be uh, IDS as in all the other cases. So VGS is 0, and ID Q point is at 10 milliamps. So there's no need to draw the transfer curve. And for the load analysis, we have VD at VDD minus IDRD, and this is also maintained at 5 volts. Right. So what varies now is then when we move to the enhancement type, is that we have some sort of a different characteristic curve. Here we do not follow the Shockley's equation, but instead uh, we base the value of the drain current from the some voltage applied at the gate to source potential rel- relative to some threshold voltage. So you're gonna have to overcome the threshold voltage for us to produce some current going through the drain, and that the relationship uh, further after or beyond the threshold voltage is described as an exponential one with the multiplier of the k factor right there. So in the case of the on condition, so in the case of a feedback bias here, the RG provides the bias to the gate, so it is maintained in the on condition. However, by definition, we have zero gate current here, no? So that VGS, and so we did not perform another loop analysis now for this thing. But in when IG is equal to zero, VRG is equal to um, zero as well, no? So we do not perform analysis in this network. And the DC, okay, so the connection exists between the drain and the gate. So here the VD is equal to VG, and that VDS is equal to VGS. So that's the convenience by drawing upon this idea that when you have zero current going through RG, because by definition IG is zero, it is a high impedance device. Um, we can assume that the voltage drop across RG is also zero, and that VD is equal to VG. So it's kind of the same thing, right? So we'll just proceed with the analysis of the output circuit. Here we have VDD minus IDRD minus VDS is equal to zero. No? So rearranging the equations, we have VGS as something that's equal to VDD minus IDRD. So for the case of zero drain current, VGS should be equal to VDD for the case of zero drain current. Substituting VGS zero, then we can have, in this case now, VDD. Uh, there should be an equation here. ID should be equal to VDD over RD, right? So there should be an equal sign right here. So I'm gonna do some sort of corrections for these slides now. Right, so try to work on some examples. For example, this case we have the drain current in the on condition at 6 milliamps, VGS at 8 milliamps. So we have a different parameters to look into when we check the data sheets. And instead of the pinch off conditions or saturation conditions, we look into the conditions where the device is turned on, right? So when the proper amount of channels is being created by the potential through the gates, or once we reach the threshold voltage. So that's why that sort of that threshold voltage should be properly defined. So once we reach the threshold voltage for the gate to source potential, that provides sufficient path so that the current can flow across the drain to source. And those are the conditions. Now, VGS on is at uh, 8 volts, threshold is at 3, and the drain current at one condition is at 6 milliamps. So we will start with the characteristic equation. No? Again, this does not follow Shockley's equation. It has its own equation using the K factor here. First is we derive the K factor since ID on is provided, VGS on, and the threshold voltage are provided. So we have the K factor at 240 times 10 to the negative 6. It has some sort of weird looking unit, but this is just some multiplier to balance things out. Uh, so the unit is at amperes per um, voltage squared, right? So uh, after that, then we can now obtain the value of. This can be useful for later calculations of drain currents. But for now, we will go through the drain to source or the output loops. Here we have VGS as equal to VDS, no, in this case. And that VDS is equal to, by the loop analysis here, as VDD minus IDRD, minus VGS is equal to 0, rearranging that we have the expression for the VGS. And that VGS is equal to 12 minus ID times 2K ohms. And so we have another expression for ID right here. Okay, so we already have the K values. We have, or the K value, we have the expression for VGS and ID. Then we can substitute this thing right here since threshold voltage is provided, so we can have the quadratic equation having the drain current as uh, your missing quadratic formula or shift solve will yield 2.79 milliamps. Applying the drain current in this condition, in the on condition, through the output loop, we have now the following. So we have VDS as equal to VDD minus IDRD. We have the 12 volts VDD, and then ID at 2.79, and then RD at 2 kilo ohms, right here. So VDS becomes 6.24 volts, meaning that we have maintained the 6 volts, 6.2 volts right here in the on condition. This is not, again, this is not seen by the VO since this is a component, but this sufficiently holds or sort of maintains that condition so that when AC input is presented, this will swing with the AC components on top of it. Right, so for the case that, okay, so alright, so for the case that the 2 points are defined, where we have the VGS on and the threshold at voltage at 3 volts, VGS on at 8 and threshold voltage at 3. So we can plot the line right here, no? Um, and the ID on at 6 milliamps. So if you're wondering what does it look like, it kind of looks like this one. Uh, so ID on is somewhere here, and the VGS on is here. So we have 2 points provided, and the threshold voltage here. Right. So okay. So considering some points in between these. So if we solve for VGS at 6 volts, so that's between 3 and 8, then the ID becomes the drain current at that point from the K value here becomes 2.16 milliamps. So we can plot the line based on these calculations. For VGS at 10 volts, you can extrapolate beyond the Q point. So it's greater than your threshold voltage. Yes, definitely. And the drain current at that point is at 11 milliamps. So that's how you can plot this curve with assuming different values of drain currents and the corresponding VGS currents. Right. So 4 points are sufficient to plot the full curve. No? Actually, we have the 3 point rule. I think you can be able to plot at least using 3 points for the exponential, 2 points for the linear, but 4 points is sufficient to generate or to give us idea on how steep the response characteristics will be in when using this equation right there. Now, for the load line analysis, we have to uh, solve for conditions of ID zero. So at ID zero, right? So for the ID zero, or at VGS zero, we have ID at 6. It was defined in the problem. And for VGS, for ID zero, we have VGS at, what's that? And so the max for the VGS is your VDD supply, no, at 12 volts. So plotting that load line, then you can have the intersection of the exponential with the load line, and that's your Q point at 2.7 milliamps and 6.4 volts, no, for the Q points. All right, so for the case of the voltage divider bias, so far we have the feedback bias. Okay, so next we have the voltage divider bias. Same thing as your JFETs. We have to solve for the voltage drop at R2 to serve as your VG right there. And that once you have the VG, then you can now solve for uh, come up with an expression for VGS now using this loop, and you can plug in that expression to your well, not your Shockley's equation, no, but the equation for your enhanced MOSFET. And then for the output section, similarly gonna solve using this loop, considering the drain resistance and the source resistance. And so, say for example, we have the following problem provided that 2N4351 MOSFET is has a threshold voltage of 5 volts, drain current in on condition at 3 milliamps, and at 10 volts VGS. Right, so first we have to solve for the K value from the equation. Everything is provided, so we just plug in all those values. So we have the K at 120, uh, 120 of a million. No? And then once you have the K value, we perform voltage divider into the input network right here, or the voltage divider network here. So the gate voltage is your R2 or the VR2. So you can see that this is say 22 and 18 is 40 mega ohms at 40 volts. You just directly apply this, then you have 18 volts right there. VGS is calculated from this loop. So at 40 volts, all right, so you can rearrange the equation to have uh, VGS expressed in terms of ID, and then you can plug in the expression of VGS into the exponential equation. So in this case, we now have the K value and a quadratic equation for the drain current. Using again quadratic formula or shift solve function, you can solve for the drain current at 6.7, and then calculating again in the input loop for the VGS, you can solve for the VGS at 12.49 volts. So this VGS maintained at 18 volts. The drop here is at 12 volts. And so VDS can be calculated as well in the output loop. Once we have the ID given, the ID calculated, so VDS becomes 14.3. Right, so to plot for the exponential curve, then we can assume different values of ID, no? But as long as you go beyond the threshold voltage, so you have the threshold at 5 volts. Right, so for the 5 volts, so you're gonna have to subtract the threshold voltage, no? So you can come up with the drain current measurements. Right, so at 10 volts, you have 3 milliamps. Uh, 15 volts, you have 12 milliamps. And at 20 volts, you have 20 milliamps. So you're just gonna plot this exponential, and of course, you have a zero current below the threshold voltage. So you can plot again the load line analysis, and at that point of intersection, then you can have the quiescent values or the Q point values. All right, so for the Q point, right, so we have the analysis. In this analysis, we have the figures of VG over RS right there. And for the case for the VG, you have VG at 18 volts for your supply. So for the Q point, we can see the intersection at 6.7 and 12.5 for ID and VGS respectively. Yeah, so I think we're gonna have to do a quick review of some of the calculations. So notice some typo before. Let me check if there are other typos here before I share. So here are some of the pertinent shortcuts now for the formulas we've covered earlier. So this is also available in the I think either front cover or back cover of your Boylston text. So kindly check on that one. And again, you may go back to the lecture manuals or modules that I've shared in the groups. So I guess that's pretty much it. No? So yeah, so that's it. And I think I posted or I shared already, the details for Q1 for the quiz one is at next week. Again, that will be MCQ for the duration of 2 to 5 p.m. And after that, after the quiz next week, we can discuss further now on the various possibilities, or arrangements, for your projects. But for now, according to my sched, then we can have some face-to-face meeting for the presentation of your project proposals or concept papers, and that will be on March 16, or any time within that week 8, March 16 or 17. Okay, so yeah, so maybe I can propose some or present some further details on that. So again, tomorrow I'll post the guidelines for Lab 1 for the presentation. But you may now start doing uh, the computation, no, for the Lab 1, or if you want to do the prototype or simulation, you can start doing this now, and documentation will follow. So just keep on. I suggest you start early with the experiments and stand by for further instructions on the documentation process. So again, that's it. I think. Are there any questions, concerns, or clarifications so far? Okay, so if none, can you see a show of hands if everything is clear up to this point? Okay, so thank you guys. No, so I suggest more practice exercises from the problems presented in our texts, and again, you may check as well the the modules and manuals that I've shared uh, in the classroom. No? So if there will be any questions or concerns, uh, just feel free to send me a message anytime. Also, I've received the emails from some excuse letters. No, I've taken note of those, although I haven't responded on your messages. No, those are noted, and that's it. No, so I'll see you guys next week, and please start working on the lab experiment one. Sorry, I'll see you still tomorrow for the AC analysis. And that's it. No? See you guys tomorrow, and have a great day ahead. And stay safe. No? See you guys tomorrow.